Alright, so again this will be 2000 volts peak, 100 microsecond full width half height with a 2 ohm source. Unfortunately, it looks like we have also damaged Dave's meter. This should be roughly 115 millivolts, and you can see it's reading quite low now. This should be roughly 500 degrees Celsius, and we can see that that no longer works. This is 50 ohms, 100 ohms. You can see they're all reading off by quite a bit. This will be 1K. Wow, look at the error now. 2.7K for a 1K. This is a 10K. You can see it's reading 358. This is with a 100K, and you can see it's now overranged. So in capacitance mode, with the leads open, this would normally be reading 0. You can see it's hunting. So unfortunately, I think that's going to be it for the video. There's not much else I could do. I could attempt to go in and try to analyze the meter. Unfortunately, I don't think I can make that information publicly available.
We have separation. Roger. Inboard and outboard, they're on. We're coming forward with the side stick. Oh, looks good. Roger. I've got a blowout. Amber 3. Get your pitch to 0. Pitch is out. I can't hold altitude. Correction. Alpha hold is off. Trim selected. Emergency. Flight comm. I can't hold it. She's breaking up. She's breaking. We can rebuild him. We have the technology. We can make him better than he was. Better, stronger, faster.
We're going to start by going through a basic functional test. Currently the meter is attached to my Fluke standard reference. The standard has not been allowed to warm up. This is with 1 volt applied. This is with 1 millivolt applied. And I'll go ahead and change it to the millivolt range. So let's just go back to the volts function. It should be 2.5, and this should be 2.5 as well. You can see currently I have the AC plus DC mode selected. This should be 5 volts. This should be 2.5, and this should be roughly 3.6. This should be roughly 115 millivolts. Now this mode did not work before. That 118 is fairly close to what I remember the meter displaying originally. Again, this should be roughly 500 degrees Celsius. And again, this function did not work before. This should be roughly room temperature. And this should be a little over 1,000 degrees. This should be 60 Hertz. This is AC coupled. This is with the DC couple and a 2.5 volt DC offset. This should be 30 Hertz. This should be 15 Hertz. This should be 120. And this should be 240 Hertz. And this is our period for a 60 Hertz waveform. And this is our duty cycle, which should be 50%. This is with our leads open. You can see it's reading overranged. This is with our 0.5 ohm resistor. You can see it is now reading pretty much dead on. Again, that 0.5 ohm is a 1% part. This is with 50 ohms. This is with 100 ohms. Again, this is a 0.01% device. This is with a 1K ohm resistor. This is with 10K ohms. This is a 100K ohm. This is with a 10 mega ohm resistor. This is with a KDAC 20 mega ohm 1% resistor. You can see I have 2 of the KDAC 20 meg parts in series, and the meter is reading fairly close with this. It's fairly sensitive to outside disturbances, but you'd expect that. This will be continuity. It seems to function right. This is in diode check. This is with a short. And this is with 3 diodes in series. You can see our open circuit voltage is roughly 3.2 volts for the diode check mode. This will enable our 15 volt mode. You can see the 15 volts in the upper right. And you can see it is now applying almost 16 volts output. And you can see we've returned to the 3 volts and we're getting roughly 3.2 out. This is in the capacitance mode, and you can see with the leads open we are reading 0.02. This will be 1 nanofarads. This is with a 0.1 microfarad. This is with a 1 microfarad. This is with 10 microfarads. And this is with 100 microfarads. So before David sent me this meter, he had provided me with the schematics for it, and of course I've agreed not to release any of that information into the public domain. Having that document ahead of the meter gave me an opportunity to analyze the design before I actually received it. So I had pointed out some of my concerns to Dave before I even hooked this up to the transient generators. Well, I think the next thing I'd like to do is have a look at why the meter failed at 2 kV and see if we can address that. So over the course of all the testing that I've done, I've modified a few meters. These are the last 3 that I modified. With this Gaussian, it was more of a mechanical modification. What I had done was fabricated a shield for it. This UT181A was also kind of more a mechanical modification. On this meter, it was basically a problem with the circuit board layout. So I ended up having to cut some traces and reroute some things with it. And that was really all that was wrong with this meter. I purchased this UT61E just for the sole purpose of modifying it, and I've been into this meter more than any other one that I've looked at. I've made a whole series of videos just on how I made those modifications, but the big problem with this meter is that it actually failed my grill starter test, just like this UT181A, and I walked you through the entire design, how it all worked, and what the problems were, and how I overcame them. If we look at the 2 circuit boards for the 2 meters, on the right we have the UT61E, and you can just see the density of the 2. There's basically hardly anything on the circuit board. It all comes down to this one control IC, and that's really it. You can see on Dave's meter there's all kinds of stuff going on this meter. Modifying this was fairly trivial compared to what it's going to take, I'm afraid, to modify this meter to make it more robust. One of the problems will be handling areas that are potentially too close to one another. If you watch the video for the UT61E, you may remember that I actually cut slits in the board to increase the clearance. Clearance is basically when we're looking at an electrical distance between 2 points through the air. Creepage would be looking at it across the surface of the circuit board. You can see that I've already got a couple of slits in it right now, but if I need to go in and add additional slits, there is just not a lot of room. Another concern I have is with the sheer number of power supplies this board has. This design has 4 different power supplies. It also has 4 different grounds. Only 2 of those grounds are actually tied together. So when I start looking at how the current flows through this board under a transient condition, there's a lot to consider. So this isn't something that's just going to be a quick fix like it was so much with this UT61E. I'm really going to have to give this some serious thought as to how to proceed. So what I've done up here is I've attempted to replicate the front end of the 121GW. These MOVs actually will break down at a little bit higher voltage than what the 121GW does. Then I have some different components that I've purchased that I want to evaluate. So I've just ran the very first one. You can see the transient generator is set for 3,500 volts. This is 1,000 volts per division. This is the yellow trace. The blue trace is the TVS that I'm evaluating. We can see that even under these conditions, the output of that seems to be just fine. So it's now strapped over to another part that I want to evaluate. And again, I'm just going to apply 5 transients to this, and we'll see if this device holds up. As you can see, it looks pretty good. The blue trace is the part we just looked at, and you can see it's quite flat. So I've reprogrammed the generator for about 5,500 volts. We'll just give it a single transient. Looks pretty good. You can see the voltage didn't go up a whole lot. What we'll do is just go ahead and apply 5 full transients to it. Alright, so it looks real good. What we'll do is switch over to the other component. Alright, we'll just go ahead and apply 5 more transients. And you can see the voltage level drops just a little bit. The reason that you see the baseline kind of moving around, I have a transformer inside of the transient generator to output the 220 volts AC. That's being driven off of a solid state relay. It has enough leakage current where I'll always get some amount of AC voltage. It's kind of residual that rides on this. You'll never see the blue line fall below ground, and that's because the output of that transformer goes through a bridge rectifier. So I would say these two parts that I'm looking at look pretty good. So I finished my modifications to the meter. I think what we're going to do is repeat the initial test. So you can see I have my Brahman BM869S on the right and the pre-production 121 GW on the left. Both these meters are attached in parallel and they're connected to the high voltage supply. So the first thing we're going to do is apply a high voltage DC to both meters, and let's just make sure that this meter will still handle that just fine. Again, I've made quite a few modifications to this meter. I just want to make sure that I didn't screw anything up. I think this thing trips at like 600 volts. Oh, right there it's starting to give us the warning. It's pretty much the limit of it. I think it's 650 volts it's going to roll over. And that's the limit of the power supply right there, so 982 volts being applied to it. And no problem. And the next thing I'd like to do is flip the polarity. It looks good. Alright, so you can see I'm outputting roughly 540 volts. See, the two meters are basically reading the same value. Let's go to AC plus DC. And you can see both meters set to AC plus DC. They both read 541 volts or so. What I'm going to do now is increase the DC bias. And you can see the 121 GW is starting to air out as I exceed its input range. And this is with a negative bias. You can see that with this meter here. You can see we're at minus 315 volts right now. That's the DC bias of the AC waveform. And again, going back the other direction. So it doesn't look like any of the modifications have affected the high voltage performance of the meter. Next we'll just be doing a full functional test of the meter. So again, this will be 5 volts DC. This should be 2.5 volts. Well, that's correct. And this should be 2.5 as well. That is correct. And this should be 3.6 roughly. Actually, if we look at the AC plus DC value of this, or roughly 2.5 squared multiplied by 2, and then take the square root, it comes up to 3.53. We could see it comes up actually fairly close to that, 3.52 roughly. This should be 2.5, and this should be 5 volts. This should be roughly 118 millivolts. And this should be roughly 500 degrees Celsius. This should be roughly 60 hertz. This is AC coupled. This is with the DC bias, so again this should be 60 hertz. This should be 30. And this should be 240. And again, this is the period. That is correct. And this should be duty cycle. That's correct. This is with 0.5 ohms, 1 ohm, 50 ohms, 100 ohms, 1K, 10K, 100K, 1 meg. Continuity test. This is our diode check. So 1 diode, 2, 3 diodes in series. And you can see the open circuit voltage is roughly 3.2. Here we've enabled the 15 volt output, and you can see we're reading roughly 15.8. Again, that's open circuited. Doesn't take a whole lot to drain this down. Let's just try it with a 100k ohm resistor. You can see it pulls it down a fair amount. This is with a 10k ohm resistor, and you can see it's really limiting the current through it. This is with 1 nanofarad. This is 0.1 microfarads, 1 microfarad, 10 microfarads, and 100 microfarads. So you can see the modifications that I've made haven't really affected the meter at all. So when this meter was supplied to me, the switch contacts were not lubricated. I've added a small amount of lubrication. Okay, so I have the meter attached to our transient generator. I'm just going to enable our AC supply, and you can see it's displaying roughly 120 volts. You can see this is roughly 240 volts DC. You can see the AC plus DC value is roughly 270 volts. What I'll do now is just rotate the knob through the remaining settings. And then I'll go ahead and functional test the meter. So the meter appears to be just fine. One of the things I'd like to show you is the upper end for the frequency. Of course, it can read the 60 Hertz just fine, all the way up to the 240 Hertz. That's the limit of this box. But let me hook this thing up to our function generator. So you can see I'm putting out roughly 992 kilohertz right now. So what I've noticed with this meter is this will roll over at 1 megahertz. It appears to be a limit of the firmware, and I don't know if they can address that. I gotta believe that the hardware could actually run up quite a bit higher than a megahertz. Let's just turn this up a little bit higher and I'll show you. See, that is the top end of the meter. Next we'll run our Esd test. This generator will put out about 4,000 volts peak in less than a nanosecond, and it'll also apply somewhere around 15 amps. It's very close to what the IEC standard calls for. And again, I'll be applying 5 transients, both positive and negative, with each mode of the meter. Alright, I'll go ahead and functional test it. So the 121 survived the Esd testing just fine. So I've got our high voltage probe out. You can see I have it attached to our Fluke 97 right now. This is currently set for 500 millivolts or 500 volts per division. And you can see we're 3 divisions up. We're going to be starting with 1.5 kV. Again, the meter previously had failed at 2 kV. So we'll be applying again 5 transients, positive and negative. Alright, so the meter passed functional just fine. That does not surprise me too much. So I've reprogrammed our generator. Boy, the glare is just terrible off the scope. So you can see we're 4 divisions up at 500 volts per division, so 2000 volts. Again, this is a 100 microsecond full width half height with a 2 ohm source impedance. So this is where the meter had failed previously. So again, we'll be repeating the same test. This will be 5 transients, positive and negative, in each mode of the meter. Alright, let's just do a real quick check. You can see we've got the 115 volts here. And there's our 240 volts. We'll just connect up our little box real quick. And let's just have a look at the temperature input. Again, this should be roughly 500 degrees. And let's try it in resistance mode. So here the leads are open. This will be our 1 mega ohm resistor. Just try her with a 1k ohm. Looks fine. Let me go ahead and finish functional testing it. Alright, so we've definitely made an improvement. The 121 GW passed that test just fine. Again, that's where it had failed the last time. So you can see I've changed our transient generator now for, you can see it's now set for 1000 volts per division. The peak is now 3 divisions up, or 3000 volts. I'm going to skip the 2500 volt increment. And again, we'll be applying 5 transients, positive and negative. And let's just do a real quick check of the resistance. And again, this will be roughly a 1K ohm. Looks pretty good. And 10K. Looks good. Here's 100 ohm. Looks good. And here's a meg. Looks good. Let's just try capacitance mode. Here's a 0.1. Looks good. Alright, let me go ahead and functional test it. Alright, so the meter passed functional just fine. Wow, the glare is just terrible. So anyway, so you can see we're still at 1000 volts per division. And you can see we are now at 4 divisions up, or roughly 4000 volts. Same as before, 5 transients, positive and negative, with each mode of the meter. Again, this is a 100 microsecond full width half height with a 2 ohm source. Again, not a whole lot of energy. At most, about 20 joules is all this generator is good for. Alright, that's it. Again, let's just do a real quick check with it. We'll enable the AC. See if that still works. Let's try it with the DC. Again, this should be about 240. That looks fine. You can see our PTCs are starting to cool down. And let's try resistance. It's with a 1 mega ohm. And you can see it's slowly drifting up as the PTCs are starting to recover. Let's try it with a 1K. It's pretty good. Let's try it with a 100 ohm. Looks good. Let's go back to the 1 meg. You can see it's getting closer. Take it a little while to recover from this. Let's try it with the 10 meg. Same thing, you can see it slowly recovering. Let's let it cool down. I'll go ahead and finish functional testing it. Okay, so the meter passes functional just fine. Again, that was a 4000 volt peak with 100 microsecond full width half height. You can see the PTCs have had quite a bit of time to cool down. Everything is basically back to normal now. So I've reprogrammed our generator to put out the maximum voltage. Again, this is about 5.8 kV, and it's the most I can get out of this thing. Without changing over to the other generator, this is the top end. Again, we'll be applying 5 transients to each mode of the meter, positive and negative. We'll see if it survives this. Okay, that's it. Let's just try the AC mode. You can see it slowly drifting up again. Again, the PTCs are going to be pretty warm. Let's try it with DC. Again, this should be about 240 volts. Looks fine. Alright, so we'll be using our test box. Again, this should be roughly 5 volts. This should be 2.5. This should be 3.5. Should be 118 millivolts. Should be roughly 500 degrees. This should be 60 hertz. And again, this is 60 Hertz with the bias. This is our period and duty cycle. This is with a short. You can see the PTCs are still cooling. Let's just try it with a 1 ohm. And 50 ohms, 100 ohms, 1K, 10K, 100K, 1 meg, 10 meg, continuity test, diode check. This is with a short. Here's with a single diode. Again, this is with the Bryman placed across the 121 GW. We can see our open circuit voltage is roughly 3.2. And this is with the 15 volt supply enabled. This is with 1 nanofarad, 0.1 microfarads, 1 microfarad. This is 10 volts coming out of our Fluke standard reference. This is with the reference set to 1 volt. And this is with the reference set for 1 millivolt. So there you go. It looks like the meter is still 100% functional. I'd say we've made some pretty big improvements with it. Alright, I think we're about ready to wrap up this video. There's a couple of last things I'd like to show you. I've showed you how it has a 15 volt diode check mode for looking at high voltage diodes. I've also showed you how it can measure AC and DC power. One of the things I haven't showed you is the low burden voltage for this meter. So this UT61E, if you followed any of my videos, this meter is highly modified, and one of the things I've done with this was try to improve the burden voltage. So these two meters are in series right now, and I've got the BM869 sitting in parallel with the 121 GW, so he's looking at the burden voltage for this meter, while the UT181A is looking at the burden voltage for the UT61E. So using our test box, we'll apply 100 microamps through these two meters. So you can see current-wise, they basically read the same. And you can see the UT61E has a burden voltage of 1 millivolt, and that's compared to 10 millivolts for the 121 GW. But again, this meter is highly modified to reduce that burden voltage. If you go back and watch the videos on this, you'll see where I've changed the shunts and I've added a chopper amplifier to this to improve it. So I'm not too surprised that this can outperform this meter. This is pretty impressive still. So let's try it with the milliamp ranges. So here you can see I'm applying roughly 920 microamps through each meter. And now we can start to see where the 121 GW is actually better than the UT61E. You can see the drop across this is 2.47 millivolts, and that's compared to 9.8 with the UT61E. So this is with 1.5 milliamps, and you can see we are dropping roughly 16 millivolts for the UT61E and 4 millivolts for the 121 GW. If we change the connector from the standard milliamp to the 500 milliamp mode, you can see how it's dropped the burden voltage even further. We are now down to about 40 microvolts compared to 16 millivolts. So here you can see we changed ranges again. We're now at roughly 35.5 milliamps, and we can see the burden voltage now for the 121 GW is 1.3 millivolts versus about 321 for the UT61E. So with roughly 100 milliamps being applied, and you can see the 121 GW is all the way down to 3.5 millivolts, and compare that with about 500 millivolts now for the UT61E. So some huge improvements with this meter, even compared to the one that I've modified. Again, I'd like to thank Dave Jones over at the EEV blog for providing me with this pre-production 121 GW. Hopefully they'll be able to use the information I've provided to improve the final design. Again, I'd like to welcome all you new followers. Well, I think that's going to be it for this video. Till the next meter. Later.